role of environment, dark matter, and supermassive black holes in shaping such extraordinary structures remains a central focus of contemporary astrophysics. Often referred to as the Titan of Galaxies, this ancient behemoth continues to inspire awe, prompting further exploration into the mysteries of the cosmos. Situated in the dense environment of the Abell 2029 cluster, this colossal system serves as a natural laboratory for studying the interplay between galaxies and their surroundings. The cluster's intracluster medium, a hot, X-ray emitting plasma, interacts with the giant elliptical, influencing its evolution and that of its satellite galaxies. Gas stripped from smaller neighbors through ram pressure interactions enriches the medium, contributing to the overall complexity of the system. These processes highlight the dynamic nature of galaxy clusters, where gravitational forces and high-energy phenomena shape the universe on vast scales. Beyond its scientific significance, this cosmic monarch serves as a reminder of the diversity and scale of the universe. Its immense size, brilliance, and central location within the Abell 2029 cluster make it a prominent cosmic landmark, a beacon of light visible across hundreds of millions of light-years. Observing this galactic titan provides a glimpse into the distant past, offering insights into the intricate interplay of forces that have shaped the cosmos. As research progresses, this ancient colossus and its analogues will remain pivotal to our quest for understanding the universe, offering a window into its boundless possibilities. The giant elliptical of Abell 2029 continues to intrigue astronomers with its sheer scale and complex history. This celestial titan, alternatively called the Abell 2029 core galaxy, stands as a testament to the immense forces at play in the universe. Measuring over 6 million light-years across, it dominates its galactic cluster in both size and influence, earning titles such as the Colossus of Virgo in astronomical discussions. This supergiant has undergone countless mergers, consuming smaller galaxies in a process that has shaped its current structure. Each interaction has added stars and gas, further enriching the galactic core. This relentless process, known as galactic cannibalism, underscores the dynamic interactions within dense cosmic environments. At its heart lies a supermassive black hole of extraordinary proportions, sometimes referred to as the gravitational anchor of Abell 2029. With a mass surpassing 40 billion suns, it is among the largest ever detected, governing the motions of stars and gas within the galaxy, while exerting influence on the broader cluster environment. The intense gravitational field of this singularity contributes to the galaxy's luminous core, radiating across vast distances, earning it epithets such as the light beacon of Virgo. The stellar population of this ancient colossus is predominantly old and yellowish, characteristic of elliptical galaxies. Most stars within this vast system exceed 10 billion years in age, marking a galaxy that has long since exhausted its supply of cold gas necessary for star formation. Instead, the stellar graveyard of Abell 2029 glows faintly with a golden hue, a visual indicator of its advanced evolutionary stage. Surrounding this interstellar monarch is a vast halo of dark matter and interstellar material, often termed the cosmic veil of Abell 2029, extending far beyond its visible boundaries. This halo influences the cluster's gravitational dynamics. Within it, intracluster light, a faint glow from stars stripped from their original galaxies, adds an ethereal quality to the region. These orphan stars, drifting through the intergalactic sea, serve as evidence of the violent history of galactic interactions that have defined the Abell 2029 monarch. The surrounding environment of this galactic elder is rich with X-ray emissions, a consequence of the hot plasma filling the Abell 2029 cluster. These high-energy phenomena, observable by Chandra and XMM Newton, reveal the turbulent conditions within the X-ray furnace of this dense system. Interactions with the cluster's tidal forces strip gas from smaller galaxies, enriching the intracluster medium and fueling the ongoing evolution of this cosmic giant. Studying this luminous elder of the universe provides unparalleled insights into galaxy formation and evolution. As one of the largest known galactic structures, it serves as a crucial subject for exploring extreme cosmic phenomena. The role of supermassive black holes, dark matter, and galactic mergers in shaping such immense systems remains a fundamental question in astrophysics, with the Colossus of Abell 2029 offering valuable clues. Despite its age and apparent dormancy in star formation, this golden leviathan continues to exert significant influence on its surroundings. Its gravitational pull dictates the movements of satellite galaxies and contributes to the broader dynamics of the Abell 2029 cluster. As the gravitational heart of Virgo, this celestial giant exemplifies the scale and power of cosmic structures, a reminder of the vast forces governing the universe. This eternal sentinel of the Virgo supercluster, sometimes referred to as the cosmic giant, stands as a silent witness to nearly the entire history of the universe. With an unfathomable size, this ancient behemoth has absorbed and consumed countless smaller galaxies, preserving a vast record of cosmic evolution within its structure. At its core lies a supermassive black hole of unimaginable scale, often described as the Abyssal King or the Dark Heart of Abell 2029. With a mass exceeding 40 billion suns, its gravitational pull is so intense that even light struggles to escape. The energy released by matter spiraling into this behemoth generates a luminous halo of X-rays, an eerie beacon that signals its presence across intergalactic space. This singularity, the cosmic anchor, dictates the structure of its host galaxy, binding stars and dark matter in an unending gravitational dance. The luminous behemoth stands as a monument to galactic cannibalism, a relentless cosmic predator. Over billions of years, it has consumed not just a few, but potentially thousands of smaller galaxies, merging their stars, gas, and dark matter into its sprawling form. These ancient collisions, some violent and others gradual, have left imprints across its vast halo, a graveyard of shattered galactic identities. Each merger has been a step toward its immense scale, making it one of the largest galaxies ever observed. Often described as the universal apex, it represents the ultimate fate of many evolving galaxies. Despite its outward stillness, this silent monarch is far from dormant. While its visible light radiates a golden hue, a testament to its aging stellar population, its hidden layers remain active. X-ray telescopes reveal a sea of hot plasma permeating the intracluster medium, a cauldron of gas stripped from neighboring galaxies via gravitational interactions. This invisible fire glows in high-energy wavelengths, exposing the turbulent forces shaping the Abell 2029 cluster. The galaxy's cosmic shroud, an immense halo extending beyond its core, envelops countless orphaned stars. These unbound celestial wanderers drift aimlessly through the cluster, their faint collective glow known as intracluster light, preserving the story of ancient galactic violence and ongoing cosmic evolution. Here, in the interplay of light and shadow, lie countless mergers, some unfolding over millions of years, others in cataclysmic bursts. Yet, it is not only its scale that makes this stellar colossus remarkable, it challenges fundamental understandings of the universe itself. How did such a massive structure form? What are the limits of galactic growth? These unanswered questions push astronomers to look deeper into the void, searching for clues within the glow of this cosmic elder. Its existence serves as a reminder that, despite its apparent stillness, the universe is an ever-evolving place of energy, motion, and transformation. The role of dark matter in shaping this cosmic sovereign cannot be overstated. Without this enigmatic, unseen force, its vast mass would not remain intact. Scientists theorize that this dark empire of the cosmos is encased in a titanic dark matter halo, stretching far beyond its luminous boundaries. This invisible structure not only binds its stars together, but also dictates the motion of galaxies within the Abell 2029 cluster. Studying dark matter in such a monumental system provides essential insights into the forces that govern the universe on the largest scales. Perhaps most hauntingly, this eternal giant offers a glimpse into the ultimate fate of galaxies like our own. Over billions of years, as galaxies collide and merge, they gradually lose their distinct forms, their spirals fading into smooth, featureless ellipses filled with aging stars. In this way, the timeless Leviathan serves as a harbinger of cosmic inevitability, offering a vision of what the Milky Way and its neighbors may one day become. Yet, despite its dominance, even this galactic juggernaut is not eternal. The universe's expansion will eventually isolate it, as neighboring galaxies recede beyond the observable horizon. Trapped in an ever-growing void, this universal colossus will gradually dim, its stars burning out, leaving behind a cold, dark remnant. But for now, it remains a beacon of knowledge, a living relic of the universe's tumultuous past. The ancient monarch of Abell 2029, one of the grandest elliptical galaxies ever discovered, is more than a single entity. It is a microcosm of cosmic history. Every star within its vast expanse, every faint whisper of gas, every drifting shadow of dark matter holds a story spanning billions of years. This stellar labyrinth challenges our perceptions of time and space, inviting us to unravel its secrets, while reminding us of the universe's boundless complexity. The sheer magnitude of this galactic behemoth, sometimes called the infinite tapestry of Virgo, places it in a class of its own. Spanning over 6 million light-years in diameter, it could only have formed in one of the densest and oldest galactic environments. The Abell 2029 cluster, a gravitational cauldron housing thousands of galaxies, provided the ideal conditions for such a titan to emerge, often referred to as the cosmic overlord. This dominant force at the cluster's core sculpts the motions of stars, gas, and galaxies across millions of light-years. At its center lies its most mysterious and formidable feature, a supermassive black hole of unimaginable scale, sometimes called the cosmic abyss. This gravitational leviathan is not merely a point of intense mass, it is a dynamic engine, consuming matter and unleashing vast amounts of energy through radiation and relativistic jets. These jets, stretching for hundreds of thousands of light-years, act as cosmic lighthouses, visible across intergalactic distances. They also reshape the surrounding environment, heating nearby gas and preventing it from cooling into new stars. The intricate relationship between this dark heart and its host galaxy is one of the many puzzles astronomers seek to unravel. The Virgo Colossus, with its ancient history and staggering scale, continues to intrigue scientists, offering a glimpse into the most extreme conditions the cosmos can produce. Every observation of this celestial titan deepens our understanding of the vast and evolving universe, reinforcing its place as one of the greatest galactic wonders ever discovered. This galaxy, sometimes poetically called the eternal jewel of the universe, stands as a relic of a bygone era, a testament to the cycle of galactic life and death across cosmic timescales. Its stars, predominantly ancient, resemble the dim embers of once bright stellar populations, collectively known as the Golden Veil of Abell 2029. These aging stars give the system its characteristic yellowish hue. The absence of young, blue stars confirms that star formation within this stellar mausoleum ceased long ago, leaving behind a tranquil but enduring celestial giant. Yet, for all its apparent serenity, this universal titan bears visible scars of its violent past. Faint trails of intracluster light, drifting remnants of past galactic collisions, surround it like ghostly echoes of long-lost galaxies. These orphan stars, stripped from their original homes, now drift aimlessly in the gravitational tides of the cluster. Observing this cosmic haze allows astronomers to reconstruct the history of mergers that have fed this stellar behemoth over billions of years. Each dim glow represents more than just a star, it is a lost galaxy, long since absorbed into the greater whole. The surrounding environment, often called the fiery realm of Abell 2029, is a place of extreme conditions. The intracluster medium, a searing plasma heated to tens of millions of degrees, fills the space between galaxies. This inferno is a direct result of gravitational energy released during galactic interactions, as smaller systems are drawn into the gravitational throne of the cluster's core. Their gas is stripped away, enriching the scorching medium. These processes shape not only the cluster's fate, but also the continued evolution of this cosmic monarch. The story of this interstellar giant unfolds across the entire electromagnetic spectrum. Radio waves reveal vast lobes of relativistic particles, remnants of past outbursts from its central black hole. Infrared surveys uncover traces of dust-silent echoes of an era when star formation was still possible. Every wavelength of light paints a different portrait, offering astronomers a multifaceted view of this infinite expanse of Abell 2029. Yet, the greatest mystery of this silent king of clusters lies in what cannot be seen. Dark matter, the invisible substance that dominates the universe's mass, plays a fundamental role in its structure. Without an immense dark matter halo encasing this stellar leviathan, its gravitational influence could not hold such a sprawling structure. Together, this invisible crown extends well beyond the galaxy's visible boundaries, binding not only its stars, but also anchoring the entire Abell 2029 cluster. The timeless Galaxies is more than just a relic, it is a symbol of the universe's relentless expansion. As space itself stretches, galaxies grow more isolated. One day, far in the future, the Abell 2029 cluster will drift so far from its cosmic neighbors that it will become an island of light in an otherwise unreachable void. The stellar empire will remain, but its surroundings will fade into darkness, a sobering reminder of the inexorable forces shaping the cosmos. Yet, in its present form, the eternal beacon of Virgo continues to shine, offering humanity a glimpse into the ultimate limits of galactic evolution. It stands as both a challenge and an inspiration, a cosmic enigma urging astronomers to push the boundaries of knowledge. Each discovery brings us closer to unraveling the mysteries of this cosmic colossus, deepening our understanding of the largest and most ancient structures in the universe. The primordial sovereign of Abell 2029, sometimes called the cosmic monarch of Virgo, is not merely a passive relic, it is a living record of the universe's history. Every star in its vast expanse, every whisper of gas, and every drifting shadow of dark matter tells a story spanning billions of years. This stellar labyrinth challenges our perceptions of time and space, inviting us to decipher its secrets and reminding us of the infinite complexity of the cosmos. The sheer size of this galactic behemoth, sometimes described as the infinite tapestry of Virgo, places it in a category of its own. Spanning over 6 million light-years, it exists only in the densest and most ancient galactic environments. The Abell 2029 cluster, a gravitational cauldron of thousands of galaxies, provided the perfect conditions for such a titan to emerge. At the heart of this vast system, the cosmic overlord dominates its region, its gravity shaping the motions of galaxies, stars, and gas across an immense scale. For all its grandeur, this celestial titan is not an immortal entity. One day, its stars will fade, its black hole will quiet, and its surroundings will slip beyond the cosmic horizon. But for now, it remains a beacon of knowledge, a monument to the forces that have sculpted the universe. Studying this stellar leviathan continues to challenge and refine our understanding of how galaxies live, evolve, and ultimately face their cosmic fate. The environment of the celestial monarch is one of extremes. The Abell 2029 cluster, a dense conglomeration of galaxies, is suffused with hot plasma that radiates X-rays detectable by telescopes like Chandra. This cosmic furnace is fueled by gas stripped from smaller galaxies as they pass through the cluster, compressed and heated by gravitational forces. These interactions enrich the intracluster medium, creating the high-energy conditions necessary for sustained X-ray emissions. For now, This timeless sentinel stands as a reminder of cosmic grandeur, a testament to the past, a guide to the present, and a vision of the universe's inevitable fate. Despite its eventual fate, the universal titan remains a source of inspiration and discovery, challenging our understanding of the cosmos. Each new observation brings us closer to uncovering not only the nature of this galactic giant, but also the fundamental forces that shape the universe itself. The primordial Colossus, sometimes revered as the king of galactic giants, stands as a monument to the immense creative and destructive forces at play in the cosmos. Its story, spanning billions of years, is a narrative of formation, destruction, and rebirth, a microcosm of the universe's constant flux. This galactic juggernaut embodies both the beauty and the violence of large-scale cosmic evolution, offering an unparalleled laboratory for exploring the mechanics of the universe. At its heart lies a region of unfathomable energy and density, a supermassive black hole, often referred to as the engine of eternity. This gravitational leviathan does more than consume, it transforms. Gas and dust drawn into its event horizon are either devoured or ejected in powerful relativistic jets, traveling near the speed of light. These outflows heat surrounding gas, preventing new stars from forming and shaping the broader structure of the galaxy. This dark monarch at the galaxy's core is both a creator and a destroyer, continuously influencing the evolution of its host. Moving outward from this gravitational abyss, the structure of the galaxy itself stands as a testament to endurance, sometimes romantically termed the stellar palace. It houses trillions of stars, many of which have long outlived their prime. These ancient suns, dimmed and reddened by time, are relics of a distant epoch when the galaxy teemed with star-forming activity. Today, their soft radiance gives the celestial elder its characteristic golden hue, a reminder of its advanced stage of evolution. Beyond this warm glow, an even more elusive component, dark matter, the silent architect of the cosmos. This unseen force envelops the galaxy, providing the gravitational cohesion necessary to maintain its vast structure. The dark halo surrounding the stellar leviathan extends millions of light-years beyond its luminous core, not only holding the galaxy together, but also influencing the entire Abell 2029 cluster. The cluster itself, sometimes described as the arena of giants, is a battlefield of cosmic interactions. Smaller galaxies, drawn toward the universal Colossus, spiral into its gravitational grip, stripped of their gas and stars before being absorbed. The remnants of these encounters are scattered throughout the cluster in the form of intracluster light, faint glimmers of stars torn from their original homes. This ghostly veil of Abell 2029 tells a silent story of galactic cannibalism, marking the violent history that has fueled the growth of this enormous system. Adding another layer of intrigue to this environment is the superheated plasma that fills the cluster's vast expanse. This cosmic furnace glows brilliantly in X-rays, revealing the turbulent processes that have shaped Abell 2029 over billions of years. Galactic collisions and mergers continuously churn this high-energy medium, keeping it at extreme temperatures. Paradoxically, this plasma, while binding the cluster together, also signals the end of star formation by preventing gas from cooling enough to condense into new stars. This delicate balance of creation and destruction defines the ecosystem of the stellar sovereign. As astrophysicists continue to probe the depths of this cosmic giant, its mysteries deepen. Each layer of its structure tells a different part of the story. The gravitational heart pulsing at its core, the ancient stellar palace glowing in quiet grandeur, the vast dark halo dictating its stability, and the luminous trails of lost stars drifting in the cluster's gravitational sea. These interwoven elements remind us that even the most massive structures in the universe are shaped by an intricate dance of forces, stretching across billions of years. Ultimately, this celestial titan stands as one of the greatest testaments to the universe's power, complexity, and endless potential. While it will one day fade into the growing void of an ever-expanding cosmos, its legacy will endure in the knowledge it provides, guiding future explorations into the nature of galaxies, black holes, and the unseen forces that govern reality itself. As we peer deeper into the stellar abyss of this galactic giant, its past becomes even more compelling. How many galaxies did it consume to reach its current size? What were the dynamics of those mergers? Astronomers have detected faint tidal streams, remnants of galaxies torn apart by its immense gravitational pull, offering glimpses into its turbulent history. Each stream, each ripple of starlight, is a chapter in a saga of cosmic dominance, written over eons. Beyond being a relic of the past, this silent titan also holds clues about the universe's future. As the cosmos continues to expand, massive ellipticals like this one provide a vision of what may become of galactic clusters in the distant future. Over billions of years, the Milky Way and its neighbors may merge into a single behemoth, much like this future vision of galactic evolution. This realization lends a personal dimension to the study of this distant leviathan, linking humanity's cosmic home to the broader narrative of time and transformation. Despite its grandeur, the eternal beacon is not immortal. Over unfathomable spans of time, its stars will exhaust their fuel, fading into remnants like white dwarfs and neutron stars. The black hole at its core, once a voracious consumer of matter, will eventually fall silent, emitting only the faintest traces of energy. In the final stages of the universe, this once luminous giant will dim into a cold, dark remnant. This inevitable fate, though sobering, is a poignant reminder that even the most colossal structures are transient in the grand design of the cosmos. Yet, for now, the stellar emperor shines on, a marvel of cosmic architecture and a testament to the power of gravity, dark matter, and time. It remains a focal point of human curiosity, pushing the boundaries of astrophysical research. More than just a galaxy, it is a monument to cosmic evolution, a beacon of the universe's ability to create both beauty and complexity on unimaginable scales. The eternal colossus of Abell 2029, sometimes called the silent architect of cosmic history, continues to captivate astronomers and philosophers alike. Spanning over 6 million light-years, this titan of the cosmos stands as a testament to the scale, complexity, and dynamism of the universe, an artifact of ancient mergers, relentless gravitational dominance, and the steady march of time. At its core lies one of the most enigmatic forces in existence, a supermassive black hole, often referred to as the abyssal monarch. This immense singularity wields a gravitational influence so profound that it dictates not only the fate of its host galaxy, but also the surrounding cluster. Matter spiraling into this void generates torrents of high-energy emissions, transforming the black hole into a beacon at the heart of a slowly aging structure. Yet, this dark sovereign is more than a consumer, it is a shaper of galaxies. As it devours matter, it releases immense radiation and energy, heating surrounding gas in a process known as feedback. This cosmic paradox, where a black hole both suppresses and sustains galactic growth, plays a crucial role in stabilizing the galactic sovereign, ensuring its continued reign over the Abell 2029 cluster. The stars of this timeless titan, often described as the golden relics of the cosmos, are among the oldest in the universe. Glowing in muted shades of yellow and red, they stand as remnants of a bygone era when the galaxy was young and bursting with stellar birth. Now, the stellar tapestry of this celestial leviathan is woven from aging giants, their fuel nearly spent, their once vibrant light fading into cosmic memory. The lack of cool gas and newborn stars gives the system its signature stillness, a tranquil facade concealing the violent history of its evolution. Encircling this ancient core is the cosmic shroud of intracluster light, a faint, ghostly glow from stars torn from their original galaxies during past mergers. These drifting cosmic vagabonds serve as spectral reminders of the many galactic bodies that were absorbed into the greater whole. By studying this stellar haze, astronomers can retrace the steps of its violent past, deciphering the collisions and mergers that built this celestial empire. Yet, the true scale of this celestial giant becomes evident when considering its dark matter halo, sometimes referred to as the invisible crown of Abell 2029. This vast, unseen structure extends far beyond its luminous core, providing the gravitational foundation necessary for its immense size and stability. More than just a binding force, this dark foundation dictates the motion of thousands of smaller galaxies within the cluster, shaping their interactions and long-term fates. Unraveling the mysteries of this halo is essential to understanding dark matter, one of the universe's most elusive and fundamental components. The Abell 2029 cluster, often described as the cosmic cauldron, is a theater of galactic interactions. Smaller galaxies, unable to resist the gravitational draw of the universal colossus, spiral toward it, stripped of gas and stars before being consumed. Their remnants linger as dim streams of light, forming what astronomers call the ghostly veil of Abell 2029. This diffuse glow is a silent record of galactic cannibalism, a testament to the relentless cycle of mergers that has shaped this enormous system. Adding to its enigmatic nature is the vast ocean of superheated plasma that permeates the cluster, known as the cosmic furnace. This X-ray bright medium, sustained by the turbulence of galactic collisions, serves as both the glue holding the cluster together and a barrier preventing new star formation. Its intense heat keeps interstellar gas from cooling, ensuring that stellar nurseries remain dormant. This delicate balance of creation and destruction defines the ever-changing fate of this stellar sovereign. As astrophysicists continue to probe the depths of this cosmic giant, its mysteries deepen. Every layer of its structure, the gravitational heart, the ancient stellar palace, the cosmic shroud of lost stars, and the vast dark halo reveals a different piece of the puzzle, each one unlocking more secrets of the universe's grand design. One day, as the universe expands ever outward, this celestial titan will stand alone, a silent witness to the passage of cosmic time. Yet even in solitude, it will remain a monument to the forces that sculpt the cosmos. Its presence in the sky serves as a challenge, urging humanity to reach further, to question deeper, and to seek the hidden mechanisms of reality. For now, the stellar emperor continues its reign, offering a window into the distant past while illuminating the pathways that lead toward the future. As long as its light reaches us, it will remind us of our place in the cosmos and the endless wonders that await discovery. The universal sovereign is not merely a component of its cluster, it governs it. Its immense gravitational pull, amplified by its dark matter halo, dictates the motions of surrounding galaxies, shaping the entire Abell 2029 system. This influence extends for millions of light years, making this colossal galaxy more than just a celestial body. It is the central anchor of a vast cosmic ecosystem. The gravitational interactions it drives ensure the cluster's ongoing evolution, fueling its dynamic and ever-changing structure. Observing this stellar colossus is a study in cosmic history and future potential. Often described as a cosmic time capsule, it holds within its vast expanse a record of nearly the entire history of the universe. Every faint stream of intracluster light, every ripple of dark matter, and every ancient star is a fragment of a grand puzzle, a silent archive chronicling the transformation of the cosmos from its infancy to the present day. This eternal beacon also offers a glimpse into the distant future. As galaxies within the Abell 2029 cluster continue to merge and evolve, this Leviathan will likely grow even larger, absorbing more matter and further consolidating its dominance. Over time, as the universe expands, this cosmic monarch will become isolated, trapped in an ever-growing void. Trillions of years from now, its stars will fade, leaving behind only remnants of cold, dark relic of a universe once filled with brilliance. For now, however, this universal titan remains a masterpiece of cosmic engineering, a living testament to the forces that shape the largest structures in existence. It challenges us to think beyond the limits of human experience, to grasp the vastness of the universe and the mysteries it holds. Every new insight into this galactic colossus brings us closer to understanding the broader workings of the cosmos. This silent titan of the cosmos, sometimes referred to as the galactic monarch of eternity, looms as an enduring enigma, a celestial fortress whose grandeur surpasses even the wildest imaginations of cosmic explorers. It invites endless speculation, stirring curiosity about the secrets hidden within its colossal structure. Spanning over 6 million light-years, this stellar leviathan exists on a scale that defies conventional understanding. To grasp its enormity is to confront the unfathomable. It could engulf thousands of galaxies the size of the Milky Way. How did this cosmic colossus attain such magnitude? Its origins are rooted in galactic collisions, mergers, and relentless cannibalism, a testament to a universe in perpetual motion, where destruction begets creation on an incomprehensible scale. At its heart, the Abyssal Emperor, a supermassive black hole of unimaginable mass, reigns over this galactic dominion, estimated at more than 40 billion times the mass of the Sun. This dark heart influences not only its host galaxy, but the entire Abell 2029 cluster. Sometimes called the cosmic maelstrom, this singularity devours matter with insatiable hunger, unleashing violent jets of energy that cut through space like cosmic spears. Yet, paradoxically, it suppresses star formation, ensuring that this ancient structure remains tranquil, undisturbed by the chaos it once fed upon. The galactic core, often described as the Golden Throne, is a dense concentration of ancient stars, their once brilliant light softened by the passage of billions of years. These stellar relics, clustered tightly in the central regions, form a radiant hub of golden hues. The absence of young, blue stars in this stellar mausoleum signals the long-dormant era of star formation. Yet, though this galaxy has aged, its influence endures, a silent architect in the grand theater of galactic evolution. Encircling the stellar monarch is its ethereal halo, a region known as the Veil of Lost Galaxies. This vast expanse of faintly glowing light consists of intracluster stars, cosmic orphans stripped from their homes during past mergers, drifting aimlessly through the void. These unbound stars remain within the gravitational grasp of the cluster, their ghostly luminescence, detectable only with the most sensitive instruments, serves as a haunting reminder of the violent history that sculpted this great cosmic entity over billions of years. Yet, the visible components of this galaxy, as immense as they are, tell only part of the story. Encasing the timeless sovereign is a dark matter halo, an unseen force that provides the structural foundation for its staggering size. This shadow crown extends far beyond its luminous boundaries, shaping not just its own fate, but that of the entire Abell 2029 cluster. Without this hidden framework, the gravity needed to bind such an immense structure together would not exist. Understanding this dark halo is key to unlocking the deeper mechanics governing the universe. The environment surrounding this eternal colossus is as fascinating as the galaxy itself. The Abell 2029 cluster, sometimes described as the cosmic battleground, is a dense region of space teeming with smaller galaxies, each navigating the gravitational currents of the colossal system. Over billions of years, these galaxies have been drawn toward the cluster's center, stripped of their gas and stars before becoming part of the expanding mass of the dominant galaxy. This cosmic furnace glows in X-rays, illuminating the ongoing high-energy processes that shape the cluster's structure. The interplay between this stellar overlord and its environment is an active and evolving process. As it continues its reign, smaller galaxies succumb to its gravitational pull, their material merging with the expanding mass of the colossus. This relentless cycle ensures that the galaxy will only grow larger, solidifying its status as the ultimate galactic predator. Yet, paradoxically, even as it consumes, it stabilizes, anchoring the cluster and preventing its galaxies from drifting into the cosmic abyss. Studying this universal titan is a lesson in cosmic fragility. The light we observe from this galaxy today is a message from hundreds of millions of years ago, a window into a past, both distant and/or inspiring. This celestial monument bridges time and space, connecting the present to the earliest epochs of the universe and offering a glimpse into its eventual fate. The story of this galactic sovereign is ultimately the story of the universe itself, a saga of relentless expansion, transformation, and survival. It stands as a reminder of the infinite possibilities that lie within the cosmos, urging us to explore, to question, and to marvel at the mysteries hidden in the depths of space. The cosmic monarch of eternity, often regarded as the eternal ruler of galactic evolution, remains both a scientific enigma and a philosophical wonder. More than just an object of study, this stellar juggernaut of Virgo continues to intrigue those who seek answers about existence, time, and the ultimate fate of the universe. This celestial leviathan is not merely a relic of the past, it is a silent storyteller, a relic of creation whispering tales from the dawn of time. The gravitational sovereign at the heart of this immense galaxy is a force beyond human comprehension, one of the largest supermassive black holes ever detected. It serves as the galaxy's central engine, consuming matter that ventures too close while unleashing immense energy. The X-ray emissions from its accretion disk reveal the staggering temperatures and chaotic forces at play within this cosmic abyss. These emissions are not merely echoes of destruction, they are windows into the deepest laws of the universe, offering astronomers invaluable insights into the nature of spacetime, gravity, and energy. Yet, the influence of this dark core extends far beyond its immediate vicinity. The energy released from the black hole radiates outward, heating gas within both the galaxy and the surrounding Abell 2029 cluster. This process, known as active galactic nucleus feedback, prevents the cooling of gas that would otherwise fuel new star formation. In this way, the cosmic maelstrom shapes the galaxy's future, halting stellar birth while ensuring its continued existence as an ancient, colossal structure. This paradox where destruction sustains longevity lies at the heart of the galaxy's evolution. As the universe expands, galaxies like this one will drift into isolation, their once thriving clusters stretching into the cosmic abyss. Trillions of years from now, the stars within this behemoth will fade, leaving behind only remnants: white dwarfs, neutron stars, and black holes. The supermassive black hole at its core, once a voracious consumer, will eventually fall silent, emitting only faint whispers of radiation as it slowly evaporates over eons. Yet, for now, this universal titan shines on, its light traversing the vast cosmic expanse, a testament to the forces that shape the grandest structures in existence. It is a monument to cosmic evolution, a beacon of the universe's ability to craft beauty and complexity on unimaginable scales. The stellar cathedral of this galactic colossus is a testament to the vast forces that have shaped it over billions of years. Within its core, some of the oldest stars in existence remain as relics of a time when this galaxy was young, filled with the raw material of creation. Now, these ancient suns cluster together in a dense, golden-hued mass, their light softened by eons of cosmic evolution. Subtle fluctuations in their brightness and motion reveal traces of past mergers, the gravitational echoes of long-lost galaxies now absorbed into this immense structure. Beyond its visible expanse, a ghostly veil stretches into the darkness, a shroud of lost galaxies, composed of stars that were stripped from their original homes during past encounters. No longer tethered to any single system, these celestial wanderers drift through the vastness of the cluster, forming what astronomers call intracluster light. This faint, ethereal glow is more than just a remnant of destruction. It is a silent, archive of the violent interactions that have defined this galaxy's relentless expansion. Encasing this behemoth is a dark matter halo, an unseen but all-encompassing scaffold of gravity that extends well beyond its luminous boundaries. Without this invisible framework, the galaxy's immense size and structure would be impossible. Its stars and gas would simply drift apart into the void. This dark foundation not only anchors the galaxy, but also shapes the motion of thousands of smaller galaxies within its cluster. Understanding this vast, hidden component remains one of the greatest challenges in modern astrophysics, as it may hold the key to unraveling the true nature of the cosmos itself. The surrounding cluster is a dynamic battlefield, where galaxies are drawn toward the gravitational might of this cosmic predator, stripped of their material, and ultimately consumed. These encounters fuel a superheated sea of plasma, a reservoir of X-ray emitting energy that illuminates the structure of the cluster. This fiery medium, sustained by eons of galactic collisions and black hole activity, reveals the turbulent processes that govern the long-term evolution of this region. Yet, despite its apparent stability, this galaxy is not immutable. Every faint stream of light, every displaced star, every trail of cosmic debris whispers of past destruction of smaller galaxies torn apart, their material absorbed, their identities lost within the ever-growing expanse of this celestial leviathan. It is both a relic of the past and a force that continues to shape the fabric of the cosmos itself. As the universe expands, this galactic titan will eventually become an isolated island of light, drifting alone in an increasingly dark and empty void. Over trillions of years, the last of its stars will fade, leaving behind only remnants: white dwarfs, neutron stars, and black holes. Its supermassive black hole, once a ravenous force of gravity, will grow silent, emitting only faint whispers of energy as it slowly decays. For now, though, this celestial monarch endures, its light reaching us across hundreds of millions of light-years, a beacon illuminating the depths of time and space. It stands as a monument to the invisible forces that shape the universe, reminder of the boundless creativity of the cosmos, and a challenge to our understanding of galactic evolution. This timeless titan inspires profound questions. How did the universe come to be? What forces dictate its fate? What role do galaxies like this play in the grander scheme of cosmic history? Every photon of light that reaches us from this immense structure carries the echoes of an ancient past, urging us to look beyond the limits of human understanding, more than just a galaxy. This stellar colossus is a symbol of cosmic endurance, testament to the grand scale of time, space, and gravitational power. It is not merely an object of study, but a celestial storyteller, whispering tales of creation, destruction, and the relentless march of time. Beyond its visible structure lies a ghostly veil of intracluster light, a diffuse, ethereal glow from countless stars that were stripped from their parent galaxies and set adrift within the Bell 2029 cluster. These orphan stars, no longer bound to any singular home, drift in the vast sea of gravitational currents, silent witnesses to the cosmic battles of creation and destruction. Their faint light is a whisper of past turmoil, a quiet testament to the violent history of mergers and interactions that sculpted this stellar colossus into the behemoth it is today. Enclosing this empire of stars is its invisible throne, a dark matter halo that defines its true scale and gravitational might. This unseen framework, composed of enigmatic particles yet to be fully understood, is the hidden foundation upon which this galaxy's dominance rests. Extending well beyond its luminous core, this massive halo anchors the entire Bell 2029 cluster, influencing the orbits of thousands of smaller galaxies and maintaining the delicate equilibrium of this vast cosmic system. The surrounding cluster, often referred to as a cosmic furnace, is a realm of high-energy interactions where galaxies collide, evolve, and ultimately succumb to the relentless pull of gravitational forces. At its core, a vast reservoir of superheated plasma glows in X-ray wavelengths, a fiery consequence of the gas stripped from infalling galaxies. This cosmic fire, fueled by the remnants of stellar explosions and galactic collisions, enriches the intracluster medium, forging new elements and reshaping the environment in a never-ending cycle of transformation. Yet, even as it reigns over the cluster, this celestial monarch is not immune to the relentless expansion of the universe. As dark energy accelerates the stretching of spacetime, galaxy clusters will drift ever further apart, their ancient light fading into the abyss. In the distant future, IC 1101 will become an isolated beacon in an empty universe, disconnected from all but the stars trapped within its gravitational embrace. Over trillions of years, its brilliance will wane. Its stars will wither into white dwarfs, neutron stars, and black holes, and its once mighty core will grow silent. Even its dark sovereign, the supermassive black hole that once shaped its destiny, will not last forever. Over unimaginable eons, it will slowly evaporate through the quiet process of Hawking radiation, disappearing into the void. The immortal sentinel, once the heart of an empire spanning millions of light years, will fade into a shadow of its former self, a cold, dark monument to an era long past. Yet, the story of this cosmic titan is not one of mere decline, but of entrance and transformation. Every collision, every merger, every upheaval that led to its formation is etched into the larger history of the universe itself. The galaxies it consumed, the elements it spread, the stars it nurtured all have played a role in shaping the cosmos. For humanity, IC 1101 is more than an astronomical curiosity. It is a mirror to our own existence. It humbles us, reminding us that our time in the cosmos is but a fleeting moment against the backdrop of eternity. Yet, it also inspires us, driving us to seek, to wonder, to push the limits of our understanding. Its golden glow carries whispers from the past, its massive halo binds together an entire cluster, and its central abyss hints at the deepest mysteries of spacetime itself. As scientists peer ever deeper into its ancient light, they uncover not just the story of a galaxy, but the story of the universe itself. IC 1101, the timeless sovereign of the stars, is more than just a remnant of the past. It is a beacon guiding us toward the future, illuminating the cosmic pathways we have yet to explore. Even as its final fate is sealed, this eternal Colossus leaves behind a legacy written in the very fabric of space and time. It reminds us that even the grandest structures are impermanent, that the universe is in a constant state of flux, and that within that impermanence lies an unparalleled beauty, a beauty that compels us to explore, to question, and to embrace the infinite possibilities of the cosmos. The story of this cosmic titan is not just the story of a galaxy, it is our story as well. In its unfathomable scale and incomprehensible history, we find both awe and belonging. It stands as a testament to the forces that shape existence, to the relentless march of time, and to the delicate balance between creation and destruction, entrance and transformation. And in that realization, we glimpse a fundamental truth. In the vast expanse of space and time, we are all part of something far greater than ourselves.
A supernova is one of the most powerful and awe-inspiring events in the universe, marking the explosive death of a massive star. These cataclysmic outbursts release more energy in a few seconds than our sun will emit in its entire lifetime, briefly outshining entire galaxies. Supernovae play a crucial role in cosmic evolution, dispersing heavy elements into space and seeding the next generation of stars and planets. There are two main types of supernovae, core collapse and thermonuclear. Core collapse supernovae occur when a massive star, at least 8 times the mass of the Sun, exhausts its nuclear fuel. Without the outward pressure of fusion, gravity causes the core to collapse, triggering a violent explosion. The remnant may form a neutron star or, if the core is massive enough, a black hole. Thermonuclear supernovae, on the other hand, happen when a white dwarf in a binary system accumulates too much mass from a companion star. This excess material triggers a runaway nuclear reaction, obliterating the white dwarf in a brilliant flash. Supernovae serve as cosmic factories for elements like iron, nickel, and gold. In fact, the calcium in our bones and the iron in our blood were forged in these stellar explosions billions of years ago. Without supernovae, the universe would lack many of the elements essential for life. Beyond their role in chemical enrichment, supernovae influence galactic dynamics. Their shock waves trigger the formation of new stars by compressing interstellar gas clouds. Some supernovae leave behind remnants like the Crab Nebula, which continues to expand centuries after the initial explosion, providing astronomers with valuable insights into stellar death and rebirth. These stellar explosions are also crucial cosmic beacons. Type Ia supernovae, for example, have a consistent peak luminosity, making them essential for measuring vast cosmic distances. By studying these standard candles, astronomers have determined that the universe is expanding at an accelerating rate, leading to the discovery of dark energy, a mysterious force driving cosmic expansion. The study of supernovae is not just a matter of astronomical curiosity, it has practical implications for Earth. A supernova occurring within 50 light-years could pose a significant threat to our planet, stripping away the ozone layer and exposing life to lethal radiation. Fortunately, no nearby stars are currently on the verge of such an explosion. Supernovae also produce some of the most exotic objects in the cosmos. A core collapse event can result in the formation of a neutron star, an ultra-dense remnant where a sugar cube-sized piece of material would weigh as much as Mount Everest. Some neutron stars become pulsars, spinning rapidly and emitting beams of electromagnetic radiation. If the collapsing core is massive enough, it forms a black hole, an object with gravity so intense that not even light can escape. The first recorded supernova visible to the naked eye was observed by Chinese astronomers in 185 CE. Since then, historical records have documented several spectacular events, including the famous SN 1054, which created the Crab Nebula, and Kepler's supernova of 1604, which shone brightly for weeks. Today, astronomers use powerful telescopes like Hubble and the Vera C. Rubin Observatory to detect and study these cosmic detonations. Supernovae also generate powerful neutrino bursts, subatomic particles that barely interact with matter. The detection of neutrinos from SN 1987A in the Large Magellanic Cloud confirmed key theories about stellar collapse and provided rare direct observational data on the inner workings of a dying star. Some supernovae challenge our understanding of stellar physics. Hypernovae, for instance, are even more energetic than regular supernovae and may be linked to long-duration gamma-ray bursts, the most intense explosions in the universe. The nature of so-called superluminous supernovae, which shine 10 times brighter than ordinary supernovae, remains an active area of research. Another mystery is the fate of Betelgeuse, a red supergiant in the Orion constellation. This massive star is nearing the end of its life and could explode in the next few thousand years, or even tomorrow. If it does, it will be visible in broad daylight from Earth, offering humanity a front-row seat to one of the most extraordinary cosmic events. Supernovae not only illuminate the past but also shape the future of astrophysics. Scientists are using advanced simulations, high-energy observatories, and gravitational wave detectors to probe the secrets of these stellar cataclysms. Understanding supernovae could help answer fundamental questions about the nature of matter, the origins of elements, and the ultimate fate of the universe. The next nearby supernova could revolutionize our understanding of the cosmos. Telescopes worldwide are constantly scanning the sky, hoping to catch the next great stellar explosion in real time. When it happens, astronomers will be ready. Supernovae are also responsible for some of the most extreme and mysterious phenomena in the universe, including magnetars. Magnetars are highly magnetized neutron stars, with magnetic fields trillions of times stronger than Earth's. These bizarre remnants occasionally release powerful bursts of X-rays and gamma rays, capable of affecting our planet's upper atmosphere even from thousands of light-years away. The origin of magnetars is still debated, but many scientists believe they are born from the most energetic core-collapse supernovae. Another intriguing class of stellar explosions is the so-called failed supernova. In these rare cases, a massive star collapses directly into a black hole without producing a visible explosion. Some astronomers have observed stars that seem to vanish without a trace, hinting that direct collapse black hole formation might be more common than previously thought. If confirmed, this could reshape our understanding of how black holes form and evolve. Supernovae are not only natural laboratories for studying high-energy physics, but they also play a role in shaping entire galaxies. When a supernova explodes, it injects vast amounts of energy into the surrounding interstellar medium. This feedback process can regulate star formation by either compressing gas clouds to trigger new star birth or dispersing gas and preventing further star formation. In extreme cases, multiple supernovae can create superbubbles, vast cavities in galaxies filled with hot, ionized gas. The Milky Way itself has been shaped by countless supernovae over billions of years. Some astronomers suspect that past supernova explosions may have influenced the evolution of life on Earth. The hypothesis of a supernova-induced mass extinction suggests that cosmic rays from a nearby explosion could have altered Earth's atmosphere, leading to climate change or increased mutation rates. While no definitive evidence links a supernova to past extinctions, isotopic traces of iron-60 found in deep-sea sediments suggest that at least one supernova occurred relatively close to Earth within the last few million years. The search for supernovae extends beyond our own galaxy. Astronomers regularly discover and analyze supernovae in distant galaxies, using powerful telescopes like the James Webb Space Telescope. These extragalactic supernovae provide crucial data for understanding the early universe, as they offer glimpses into the lives and deaths of the first generations of stars. Some of the earliest supernovae may have contributed to the reionization of the universe, a period when the first stars and galaxies transformed the cosmos from a dark, neutral state into the bright, structured universe we see today. The interplay between supernovae and cosmic rays is another fascinating area of research. Supernova remnants, like the famous Tycho and Cassiopeia A remnants, are believed to be primary accelerators of cosmic rays, high-energy particles that travel near the speed of light. When these charged particles collide with the interstellar medium, they produce gamma rays, which can be detected by space telescopes. Understanding the origins of cosmic rays could shed light on some of the most energetic processes in the universe. In recent years, astronomers have begun using machine learning and artificial intelligence to detect and classify supernovae more efficiently. Automated surveys like the Zwicky Transient Facility, ZTF, and the upcoming Legacy Survey of Space and Time, LSST, are expected to discover thousands of new supernovae every year. These vast datasets will help refine theoretical models and potentially uncover new, exotic types of stellar explosions that defy current classification. Another breakthrough in supernova studies came with the advent of gravitational wave astronomy. When two neutron stars collide, a process often initiated by a supernova, they produce both a visible explosion, called a kilonova, and gravitational waves, ripples in spacetime first predicted by Einstein. The detection of gravitational waves from the neutron-star merger GW170817 confirmed that kilonovae are responsible for creating heavy elements like gold and platinum, solving a long-standing astrophysical mystery. As technology advances, astronomers hope to capture a supernova in the earliest stages of its explosion, something that has rarely been observed in real time. Supernova early warning systems, which monitor nearby stars for pre-explosion activity, may soon allow scientists to predict and study these stellar deaths as they unfold. If successful, such efforts could provide unprecedented insights into the final moments of massive stars. Even in death, supernovae continue to shape the universe in ways we are only beginning to understand. Their explosive legacies live on in the stars that form from their remnants, in the elements that compose planets and life itself, and in the mysteries they leave for future generations to explore. Supernovae are not just violent endings, they are also cosmic rebirths, setting the stage for the next generation of stars, planets, and even life. The elements forged in these titanic explosions, carbon, oxygen, silicon, iron, and countless others, become the building blocks of everything we see around us. Every atom in our bodies heavier than hydrogen and helium was, at some point, created in the heart of a massive star and released into space by a supernova. In this sense, we are all made of stardust. One of the most enigmatic consequences of supernovae is the creation of exotic objects like quark stars, a hypothetical state of matter even denser than neutron stars. Some physicists speculate that under extreme pressure, neutrons in a collapsed star could break down into their constituent quarks, forming an incredibly compact remnant. While no confirmed quark stars have been observed, ongoing studies of unusually massive neutron stars suggest that these strange objects might exist. Supernovae are also responsible for some of the most luminous transient events in the cosmos. One such phenomenon is the parainstability supernova, a rare explosion that occurs in extremely massive stars, at least 150 times the mass of the Sun. Unlike typical core-collapse supernovae, which leave behind a remnant, parainstability supernovae completely annihilate the star, leaving no black hole or neutron star behind. These colossal explosions were likely more common in the early universe when massive first-generation stars dominated. Another fascinating class of explosions is the so-called zombie or repeating supernova. Some supernovae, like the peculiar IPTF-14HLS, have defied expectations by exploding multiple times over several years instead of fading away. This challenges existing models of stellar death and suggests that some massive stars may undergo prolonged, episodic eruptions before finally collapsing for good. Supernova remnants, though often associated with destruction, can also be sites of intense astrophysical activity. Pulsar wind nebulae, for instance, form when a rapidly spinning neutron star, or pulsar, injects high-energy particles into its surrounding environment. One of the most famous examples is the Crab Nebula, which houses a central pulsar that rotates 30 times per second, emitting beams of radiation that sweep across space like a cosmic lighthouse. The effects of supernovae extend far beyond their immediate surroundings. Some researchers believe that the cosmic rays generated by supernovae may have influenced Earth's climate over geological timescales. The hypothesis, known as the cosmic ray climate connection, suggests that variations in supernova activity in our galactic neighborhood could affect cloud formation and, consequently, global temperatures. If true, this would mean that the history of life on Earth has been subtly shaped by distant stellar explosions. From a technological standpoint, the study of supernovae has led to innovations that extend beyond astrophysics. The techniques developed to detect and analyze supernovae, such as advanced image processing, machine learning, and high-energy particle detection, have applications in medical imaging, nuclear physics, and even materials science. The hunt for neutrinos from supernovae has also inspired the construction of massive underground detectors, which are now used for monitoring nuclear activity and searching for rare particle interactions. Looking forward, astronomers are eagerly anticipating the next nearby supernova, as it would provide an unprecedented opportunity to study these cosmic explosions up close. Some candidates, like Betelgeuse and Eta Carinae, are closely monitored for signs of impending collapse. When the next supernova occurs in the Milky Way, it will not only be a spectacular sight but also a moment of scientific discovery, potentially answering long-standing questions about stellar evolution, nucleosynthesis, and the nature of extreme matter. As we peer deeper into the universe with increasingly sophisticated telescopes, we continue to uncover new mysteries about these celestial explosions. Each supernova, whether a fiery death or a rebirth of cosmic matter, tells a story of transformation, destruction, and creation, a cycle that has shaped the universe for billions of years and will continue to do so for eons to come. Supernovae are also key players in the cosmic web, the vast structure of galaxies, filaments, and voids that define the large-scale architecture of the universe. When a supernova explodes, it not only enriches its host galaxy with heavy elements but also injects immense kinetic energy into the interstellar medium. This energy influences star formation rates and can even drive galactic winds, powerful outflows of gas that regulate a galaxy's growth and evolution. In extreme cases, these winds may strip galaxies of their star-forming material entirely, leading to the eventual death of a galaxy. Some of the most puzzling supernovae are those associated with gamma-ray bursts, GRBs, the most energetic explosions known. Long-duration GRBs are thought to arise from the deaths of particularly massive stars, where the collapsing core forms a rapidly spinning black hole. This process generates twin jets of relativistic plasma that pierce through the dying star, releasing an immense burst of gamma rays detectable across billions of light-years. GRBs are so powerful that a single event can briefly outshine all the stars in its host galaxy combined. Scientists are still unraveling the precise mechanisms behind these extreme events and their role in shaping the universe. Another fascinating phenomenon linked to supernovae is the presence of runaway stars. These are high-velocity stars that have been ejected from their home systems due to a supernova explosion. When a massive star in a binary system explodes, the sudden loss of mass can send its surviving companion hurtling through space at incredible speeds. Some runaway stars are traveling so fast that they may eventually escape the Milky Way entirely, becoming intergalactic wanderers. Supernovae also play a crucial role in one of the biggest mysteries in cosmology, dark energy. Observations of type Ia supernovae in distant galaxies revealed that the universe's expansion is not slowing down due to gravity but is instead accelerating. This groundbreaking discovery, which earned the 2011 Nobel Prize in Physics, suggested the existence of dark energy, an unknown force that makes up roughly 70% of the universe. Without supernovae acting as cosmic mileposts, this revelation about the fundamental nature of the cosmos might never have been made. Even within our own solar system, evidence of past supernovae can be found. Scientists have discovered traces of iron-60, an isotope produced in supernovae, embedded in Earth's deep-sea sediments, on the Moon, and even in Antarctic ice. These findings suggest that one or more nearby supernovae may have occurred within the last few million years, possibly influencing Earth's environment in subtle ways. Some researchers speculate that these explosions may have contributed to evolutionary changes by increasing mutation rates or altering atmospheric chemistry. The future of supernova research is brighter than ever. Upcoming space missions, such as the Nancy Grace Roman Space Telescope, will survey the sky for new supernovae, helping refine our understanding of dark energy and the expansion of the universe. Meanwhile, ground-based observatories like the Extremely Large Telescope, ELT, will allow astronomers to study supernova progenitors in unprecedented detail, potentially identifying stars on the brink of explosion before they go supernova. One of the most ambitious projects in astrophysics today is the effort to detect a supernova in real time from its earliest moments. By monitoring massive stars with space-based observatories and neutrino detectors, scientists hope to catch the very first signals of a supernova, before the explosion even becomes visible. This would allow for an unparalleled observational campaign, capturing every stage of the event as it unfolds. Supernovae are reminders that the universe is dynamic, ever-changing, and interconnected in ways we are only beginning to grasp. From their role in forging the elements that make up planets and life to their influence on the evolution of galaxies and the expansion of the cosmos, these stellar explosions are among the most important and awe-inspiring phenomena in nature. The next supernova could be discovered at any moment, and when it does, it will undoubtedly bring new insights into the workings of the universe. Supernovae are also linked to some of the most extreme astrophysical environments in the universe, including accretion disks around black holes and the violent interactions within dense star clusters. When a supernova occurs in a crowded stellar environment, such as a globular cluster or the core of a galaxy, the energy released can disrupt surrounding stars, trigger new waves of star formation, or even influence the motion of nearby black holes. Some astronomers believe that repeated supernova explosions in the centers of galaxies may play a role in feeding the supermassive black holes that reside there, providing them with the matter needed to grow. Another intriguing connection between supernovae and black holes comes from the study of so-called fallback supernovae. In these cases, the initial explosion is not strong enough to fully eject the star's outer layers, causing some of the material to fall back onto the collapsed core. This process can lead to the formation of a black hole rather than a neutron star and may explain why some black holes appear to be born with unexpectedly high masses. The study of fallback accretion is helping astrophysicists understand the distribution of black hole masses and the conditions under which they form. Beyond individual stars and galaxies, supernovae may also have had profound effects on the early universe itself. During the first few 100 million years after the Big Bang, the universe was filled with primordial hydrogen and helium, with little to no heavier elements. The first generations of supernovae, originating from massive population 3 stars, were responsible for producing the first heavy elements, fundamentally altering the composition of the cosmos. Without these early supernovae, later generations of stars, capable of forming planetary systems and eventually life, would never have been possible. Interestingly, supernovae may also act as natural laboratories for testing the fundamental laws of physics. The extreme conditions inside an exploding star push the boundaries of our understanding of nuclear physics, particle interactions, and even the behavior of gravity under extreme densities. For example, the study of neutrinos from supernovae provides insights into weak nuclear interactions, while observations of supernova remnants offer constraints on alternative theories of gravity that go beyond Einstein's general relativity. One of the most exciting developments in modern astrophysics is the growing capability to study supernovae across multiple wavelengths and messengers. Traditionally, supernovae were studied using visible light, but today, astronomers also observe them in X-rays, gamma rays, radio waves, and even through gravitational waves and neutrinos. This multi-messenger approach allows for a more complete picture of the explosion, revealing details about the supernova structure, the nature of its progenitor star, and the dynamics of the surrounding environment. For example, some supernovae produce powerful radio emissions long after the explosion has faded from visible light. These radio signals provide clues about the interaction between the supernova ejecta and the surrounding interstellar medium. In some cases, they reveal the presence of dense, previously undetected stellar winds or companion stars that shaped the explosion. Similarly, infrared observations are crucial for studying supernovae hidden behind thick clouds of dust, which would otherwise remain invisible to optical telescopes. The role of supernovae in planetary system formation is another area of active research. Some scientists believe that shockwaves from nearby supernovae may have triggered the collapse of the molecular cloud that eventually formed our solar system. Isotopic anomalies in meteorites, particularly the presence of short-lived radioactive isotopes like aluminum-26, suggest that a supernova explosion may have enriched the early solar nebula, influencing the chemical composition of the planets and potentially even playing a role in the conditions that led to life on Earth. Looking even further into the future, some researchers speculate about the eventual fate of supernovae in an aging universe. As star formation slows down over cosmic timescales, the rate of supernovae will decline as well. However, even in a far future universe dominated by long-lived, low-mass stars, some forms of stellar explosions may still occur. White dwarf mergers, for instance, could continue producing Type Ia supernovae for trillions of years, providing one of the last sources of energy and illumination in an increasingly dark and quiet cosmos. Despite all that we have learned, supernovae continue to surprise astronomers with unexpected behaviors and exotic variations. Some stars defy predictions by exploding at lower or higher masses than expected, while others produce unusual light curves that challenge existing models. The discovery of new classes of supernova-like explosions, such as fast blue optical transients, FBOTs, and calcium-rich transients, suggests that our understanding of stellar deaths is still incomplete. Each new supernova observed adds another piece to the puzzle, helping refine our knowledge of how stars live and die. The study of supernovae is not merely an academic pursuit, it has profound implications for our understanding of the universe and our place within it. From the origins of elements to the fate of galaxies, from the mysteries of dark energy to the physics of extreme matter, these stellar explosions hold the keys to some of the biggest questions in science. As new telescopes, detectors, and technologies come online, the next generation of astronomers will continue uncovering the secrets hidden within these cosmic firestorms, ensuring that the story of supernovae is far from over. Supernovae also serve as cosmic time capsules, preserving information about the physical conditions of the universe at different epochs. By studying the remnants of past explosions, astronomers can reconstruct details about the environment in which these stars lived and died. In some cases, supernova remnants contain traces of interactions with dark matter, offering a potential observational window into one of the greatest mysteries in modern physics. One of the most fascinating and poorly understood aspects of supernovae is their potential connection to fast radio bursts, FRBs. These mysterious millisecond-long bursts of radio waves originate from distant galaxies and often appear to be linked to magnetars, which are themselves the remnants of core-collapse supernovae. Some scientists propose that certain FRBs may be caused by highly energetic processes occurring in young, highly magnetized neutron stars. If this connection is confirmed, it would provide another compelling example of how supernovae continue to shape the universe long after their initial explosion. Beyond their immediate astrophysical impact, supernovae have left a lasting imprint on human culture and history. The observation of bright supernovae in the night sky has been recorded in ancient Chinese, Japanese, and Middle Eastern texts. The most famous example is SN 1054, which created the Crab Nebula and was documented by astronomers across multiple civilizations. More recently, the supernova of 1572, observed by Tycho Brahe, helped challenge the prevailing Aristotelian view that the heavens were unchanging, contributing to the scientific revolution. Modern supernova discoveries continue to captivate both scientists and the general public. The advent of citizen science projects, such as the Supernova Hunters Initiative, allows amateur astronomers to participate in the discovery and classification of supernovae. With automated surveys scanning the sky every night, it is now possible for non-professionals to play a role in identifying these cosmic explosions in near real time. The growing importance of artificial intelligence, AI, in supernova research cannot be overstated. Machine learning algorithms are now used to sift through massive amounts of astronomical data, identifying supernova candidates far faster than human observers. These AI-driven techniques allow researchers to detect rare and unusual supernovae that might otherwise be overlooked. In the coming years, AI-powered sky surveys, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, are expected to catalog millions of supernovae, providing an unprecedented statistical view of stellar explosions across cosmic history. One of the most pressing open questions in astrophysics is how supernovae influence galactic habitability. While supernovae enrich the cosmos with life-essential elements, they can also pose existential threats to life on planets. If a supernova occurs too close to a planetary system, the resulting radiation and cosmic rays can strip away planetary atmospheres, disrupt biological processes, and potentially lead to mass extinctions. Understanding the frequency and distribution of supernovae helps scientists assess the long-term viability of habitable worlds in the Milky Way and beyond. Despite their destructive potential, supernovae may have also played a role in catalyzing life. Some hypotheses suggest that cosmic rays from supernovae could have influenced the chemistry of early Earth's atmosphere, helping to generate the building blocks of life. Other theories propose that the radiation from a nearby supernova could have driven evolutionary changes by increasing mutation rates, potentially accelerating the development of complex organisms. Looking ahead, future supernova research will likely focus on identifying progenitor stars before they explode. Recent observations suggest that some red supergiants undergo dramatic changes in their final years, such as shedding large amounts of mass or experiencing brief bursts of increased brightness. If astronomers can identify a star on the verge of going supernova, it would allow them to observe the explosion in unprecedented detail, potentially solving lingering questions about the exact mechanisms that trigger stellar collapse. The first-ever detection of a supernova in real time from its pre-explosion phase would mark a groundbreaking achievement in astronomy. Such an event would allow scientists to test predictive models, refine early warning systems, and possibly even observe new, unexpected physics. The combination of high-resolution telescopes, gravitational wave observatories, and deep space neutrino detectors is bringing us closer than ever to achieving this goal. Supernovae are more than just spectacular explosions, they are engines of cosmic transformation. Their impact spans the smallest subatomic interactions to the largest structures in the universe. Each new discovery brings us closer to answering fundamental questions about the origin of elements, the behavior of matter under extreme conditions, and the ultimate fate of the cosmos. The next supernova, whether in our galaxy or a distant one, will add another chapter to this ongoing story, revealing new insights into the life cycle of stars and the ever-evolving tapestry of the universe. Supernovae are not just isolated cosmic events, they are deeply interconnected with the formation and evolution of galaxies on grand scales. The sheer energy released by these stellar explosions can shape the interstellar medium, drive powerful shock waves, and regulate star formation over billions of years. Some of the most dramatic examples of this influence can be seen in starburst galaxies, where an exceptionally high rate of star formation leads to frequent supernovae that, in turn, generate massive outflows of gas and cosmic rays. In some cases, the cumulative effect of many supernovae can lead to the creation of large-scale galactic structures known as superbubbles. These are enormous cavities in the interstellar medium, often spanning hundreds of light-years, where the combined explosions of multiple supernovae have pushed away surrounding gas. Some of these superbubbles act as hotbeds for new star formation, while others may deplete a galaxy of its gas, effectively shutting down future stellar birth. Supernova-driven winds may also play a crucial role in determining whether a galaxy can sustain life-bearing planetary systems. If a galaxy experiences too many supernovae in rapid succession, the intense radiation and cosmic rays could make it difficult for planets to maintain stable atmospheres. On the other hand, too few supernovae would result in a lack of heavy elements necessary for planet formation. Understanding this balance is essential for estimating the number of potentially habitable worlds in the universe. One of the most intriguing ideas emerging from supernova research is the concept of galactic habitable zones. Just as the habitable zone around a star determines where planets can sustain liquid water, the habitable zone within a galaxy is thought to define regions where planetary systems have the best chance of developing life without being sterilized by supernovae. In the Milky Way, our solar system lies in a relatively stable region, safely distant from the galactic center, where frequent supernovae and other high-energy events might be hazardous to life. At a more fundamental level, supernovae continue to challenge our understanding of physics itself. Recent studies suggest that some supernovae may produce exotic particles beyond the standard model, such as axions or sterile neutrinos, which are hypothesized candidates for dark matter. If these particles are ever detected in the remnants of supernovae, it could revolutionize our understanding of the fundamental forces that govern the universe. Another open question in astrophysics is how certain supernovae give rise to kilonovae, explosions that occur when neutron stars merge. These events, first confirmed through the detection of both gravitational waves and electromagnetic radiation from the neutron star merger GW170817, provide strong evidence that neutron star collisions are responsible for producing many of the universe's heaviest elements, including gold, platinum, and uranium. The connection between supernovae, neutron stars, and kilonovae remains an active area of research, with each discovery shedding light on the complex life cycles of stars. The increasing precision of gravitational wave observatories, such as LIGO, Virgo, and CAGRA, is allowing astronomers to probe deeper into the physics of stellar explosions. If a supernova were to occur in the Milky Way today, gravitational wave detectors might be able to pick up signals from the violent core collapse itself, providing an entirely new way to study these cosmic events. This would be a groundbreaking achievement, as it would allow scientists to directly observe how matter behaves under the extreme conditions present during a supernova. Another exciting frontier in supernova research is the study of their role in the cosmic matter cycle. When a star explodes, it sends vast amounts of gas, dust, and metals back into space, where they eventually mix with interstellar clouds. This process enriches future generations of stars and planetary systems with the materials needed for life. Some of the elements ejected by supernovae eventually form new planets, while others drift through the cosmos for billions of years, becoming part of future nebulae, stars, or even intergalactic space. Looking toward the future, upcoming telescopes such as the Extremely Large Telescope (ELT) and the Square Kilometre Array (SKA) will revolutionize our ability to study supernovae in unprecedented detail. These next-generation observatories will allow astronomers to probe the earliest supernovae in the universe, revealing insights into how the first galaxies evolved. They will also help identify the most distant and energetic explosions, potentially uncovering new classes of supernovae that challenge existing theoretical models. Despite centuries of study, supernovae remain one of the most dynamic and enigmatic phenomena in astrophysics. Each new discovery adds to our understanding of the cosmos, revealing the intricate connections between stellar evolution, galaxy formation, and the very fabric of space and time. The next great breakthrough in supernova research could arrive at any moment, perhaps from a nearby explosion that lights up the night sky, or from a faint signal buried deep in astronomical data, waiting to be uncovered. Whatever the future holds, one thing is certain: supernovae will continue to illuminate the universe, both literally and figuratively, for generations to come. Supernovae are also crucial in the study of intergalactic enrichment, the process by which heavy elements produced in stellar explosions escape galaxies and spread into the vast cosmic voids between them. Observations of distant gas clouds have revealed traces of elements like oxygen, carbon, and iron, clear evidence that material ejected by supernovae has traveled far beyond its original galactic home. This process of enrichment influences the chemistry of future galaxies and helps shape the large-scale evolution of the universe. One of the most profound ways in which supernovae influence the cosmos is through their role in regulating the formation of stars. In dense molecular clouds, supernova shock waves can compress gas, triggering gravitational collapse and leading to the birth of new stars. This phenomenon is often observed in star-forming regions such as the Orion Nebula, where shock fronts from past supernovae have left behind intricate patterns of glowing gas and newly formed stellar clusters. In contrast, in some cases, particularly violent supernova-driven winds can sweep away gas from a galaxy entirely, suppressing star formation for millions of years. In dwarf galaxies, which have weaker gravitational holds, supernovae can play an even more dramatic role. A single powerful supernova or a series of explosions in rapid succession can eject a significant fraction of a small galaxy's gas, starving it of the raw material needed to produce new stars. Some scientists suggest that such supernova-driven outflows may explain why many dwarf galaxies contain so few heavy elements compared to their larger counterparts. This mechanism also contributes to the broader understanding of why certain galaxies stop forming stars altogether, a key aspect of galaxy evolution. Beyond shaping galaxies, supernovae may also leave behind long-lasting cosmic footprints in unexpected places. Some researchers have proposed that supernova remnants could be linked to mysterious ultra-high-energy cosmic rays, the most energetic particles observed in nature. These particles, which travel at nearly the speed of light, bombard Earth constantly, yet their origins remain uncertain. If supernova remnants, particularly those involving young neutron stars or magnetars, are confirmed as sources of these extreme cosmic rays, it would provide a major breakthrough in high-energy astrophysics. On a more speculative front, some scientists have even explored the idea that supernovae could be used as natural astrophysical laboratories for testing the behavior of matter under conditions impossible to replicate on Earth. The immense pressures and temperatures inside an exploding star allow for nuclear reactions that go beyond what is possible in human-made particle accelerators. By studying the spectral signatures of elements produced in supernovae, physicists can refine models of nuclear fusion, helping to understand the forces that govern both stellar evolution and the nature of matter itself. Supernovae are also thought to play a role in the evolution of magnetic fields on cosmic scales. The powerful plasma flows generated by supernova explosions can twist and amplify magnetic fields within galaxies, potentially contributing to the large-scale magnetic structures observed in the Milky Way and beyond. Some theories suggest that repeated cycles of star formation, supernova explosions, and gas mixing over billions of years may have helped generate and sustain the magnetic fields that permeate entire galaxies. Another growing area of research is the study of failed supernovae, a rare but fascinating outcome where a massive star collapses into a black hole without producing a visible explosion. In these cases, rather than triggering a brilliant flash, the star simply disappears from view, leaving behind an event horizon from which no light can escape. If scientists can identify more examples of such disappearing stars, it would provide a new window into black hole formation and help constrain the limits of stellar collapse. The continued observation of supernovae across different wavelengths has also revealed surprises about their environments. In some cases, astronomers have detected strong X-ray and radio emissions from supernovae interacting with unexpectedly dense surroundings. These observations suggest that some massive stars undergo intense episodes of mass loss in the years or even months before they explode. This challenges traditional models of stellar death, which assume a more gradual evolution toward the final explosion. With the advent of next-generation space telescopes like the James Webb Space Telescope, JWST, astronomers are now capable of detecting the faint infrared signatures of supernovae in the early universe. This allows researchers to probe some of the very first stellar explosions that occurred after the Big Bang, providing a glimpse into how the first galaxies were enriched with heavy elements. Such studies are crucial for understanding the transition from the primordial universe, composed mostly of hydrogen and helium, to the complex, chemically rich cosmos we see today. In the coming decades, artificial intelligence and machine learning will play an even greater role in supernova research. AI-driven algorithms are already helping astronomers detect and classify supernovae in real time, sifting through vast amounts of sky survey data to identify new explosions as they happen. As technology advances, AI may even be able to predict supernovae before they occur by analyzing subtle changes in the brightness and behavior of massive stars. The potential for discovering entirely new types of stellar explosions remains high. Some theorists have proposed the existence of supernova imposters, events that resemble supernovae in brightness but do not completely destroy the star. These transient events, sometimes linked to massive eruptions in luminous blue variables, LBVs, highlight the diverse and still poorly understood ways in which stars can end their lives. Perhaps most exciting of all is the possibility of witnessing a nearby supernova in our lifetime. If a star like Betelgeuse were to explode, it would become one of the brightest objects in the night sky, visible even during the day. Such an event would provide an unprecedented opportunity for astronomers to study a supernova in exquisite detail, capturing its evolution from the first moments of collapse to the formation of its remnant. Given the unpredictability of stellar death, the next major supernova could happen at any time, in any galaxy, or even in our cosmic backyard. Supernovae remain one of the most powerful forces in the universe, shaping everything from the smallest particles to the grandest cosmic structures. They are the creators of elements, the sculptors of galaxies, and the engines of cosmic evolution. As our observational tools and theoretical models continue to improve, the mysteries of these stellar titans will gradually be unveiled, revealing even deeper connections between the life and death of stars and the unfolding story of the cosmos. Supernovae also hold the potential to reshape our understanding of time, space, and fundamental physics. Some of the most extreme supernovae, particularly those involving the formation of black holes, may generate exotic effects such as time dilation due to intense gravitational fields. Studying these events allows astrophysicists to test Einstein's general relativity in extreme conditions, pushing the boundaries of what we know about the nature of spacetime itself. One particularly fascinating aspect of supernovae is their ability to act as cosmic lighthouses for deep space exploration. The immense brightness of certain supernovae, particularly type Ia, allows astronomers to measure cosmic distances with remarkable accuracy. These standard candles have been instrumental in refining our understanding of the Hubble constant, which describes the expansion rate. However, recent measurements have revealed inconsistencies in the exact value of this constant, leading to the so-called Hubble tension. The discrepancy suggests that there may be unknown physics at play, possibly hinting at new forces or undiscovered properties of dark energy. The connection between supernovae and dark energy remains one of the greatest unsolved mysteries in cosmology. The discovery that the universe's expansion is accelerating, rather than slowing down, was made through careful observations of distant type Ia supernovae. These measurements revealed that a previously unknown force, now called dark energy, dominates the universe, driving galaxies apart at an ever-increasing rate. Understanding the precise nature of dark energy requires continuous refinement of supernova observations, pushing astronomers to discover ever more distant explosions at the very edges of the observable universe. Supernovae are also central to the search for extraterrestrial life. While their destructive power can be lethal to planets in close proximity, their role in spreading essential elements across galaxies makes them indispensable to the emergence of life. The balance between these two effects, the potential for devastation versus enrichment, plays a key role in determining which parts of the universe are most hospitable to life. Some researchers believe that the periodic occurrence of supernovae in the Milky Way may have influenced Earth's biosphere, triggering evolutionary leaps or even mass extinctions. Recent studies suggest that supernovae may have left signatures in Earth's geological record. For instance, layers of iron-60 isotopes found in ocean sediments indicate that nearby supernovae likely affected Earth's atmosphere within the past few million years. These cosmic events could have altered the planet's climate, increased radiation exposure, or even contributed to minor extinctions. Understanding how frequently such nearby explosions occur, and their potential impact on planetary systems, will help scientists assess the long-term habitability of Earth and exoplanets alike. Another tantalizing avenue of research is the potential role of supernovae in triggering planetary system formation. The shock waves from supernovae have been observed to compress gas clouds, setting off the collapse that leads to star and planet formation. Some scientists hypothesize that our own solar system may have formed in the aftermath of a nearby supernova. The presence of certain radioactive isotopes in meteorites supports this theory, suggesting that a supernova explosion may have seeded our early solar nebula with the heavy elements that would eventually form the Sun, Earth, and the other planets. From an observational standpoint, astronomers are constantly refining methods for detecting supernovae in the earliest moments of explosion. Recently, several shock breakout events, brief flashes of ultraviolet and X-ray radiation marking the first moments of a supernova, have been detected, providing crucial insights into the structure of dying stars before they explode. Catching these initial bursts in real time remains a major goal of modern astrophysics, as they provide a rare glimpse into the final instance of stellar collapse. Perhaps even more mind-bending is the possibility that some supernovae could produce exotic remnants beyond neutron stars and black holes. Some theorists have speculated about the existence of strange stars, composed of even more fundamental particles called strange quarks. These hypothetical objects would be more compact than neutron stars but not quite black holes, offering a new window into the behavior of matter under extreme pressures. The future of supernova research is incredibly promising. With the upcoming launch of advanced space telescopes and the continued expansion of ground-based surveys, astronomers will soon be able to study these cosmic events in greater detail than ever before. The Vera C. Rubin Observatory's LSST will revolutionize